Ladies and gentlemen, now we will start the sixth lecture of the improve phase. During the lecture, the following topics will be covered: minimum safe batch size, total productive maintenance, mistake proofing and prevention, poka-yoke, work cell optimization. Because batching can have such a large effect on variability, and hence performance, setting batch sizes in a manufacturing system is a very important control. The batch size is often set by management based on the economic batch quantity formula, EBQ, or the demand for a fixed time period, for example a month's worth, a week's worth, etc. Both methods result in lead times and inventory levels that are generally from 30% to 80% larger than the requirement of the process. In order to have a lean system operating at peak efficiency with lowest cost, you should compute the minimum safe batch size from the formula shown here. Types of process batching: serial batching, processes with sequence-dependent setups. Batch size is number of jobs between setups. Batching used to reduce loss of capacity from setups. Parallel batching, true batch operations, for example, heat treat, painting, shrink wrapping. Batch size is number of jobs run together. Batching used to increase effective rate of process. Basic economic batch quantity, EBQ, is a measure used to determine the quantity of units that can be produced at the minimum average costs in a given batch or products run. EBQ is basically a refinement of economic order quantity mode, EOQ, in order to take into account circumstances in which the goods are produced in batches. The goal of calculating EBQ is that the product is produced in the required quantity at the lowest cost. The table shows the setup and processing time per unit are held constant, whilst the lot size is changed. The ratio is the percentage increase in effective operating time caused by the setup time. If setup takes a long time, then lost production due to setup drives up cost of the actual production itself. The smaller lot size, the higher the ratio of the setup time. Lot size of 100 will take only 5.8 minutes operation time per item, with ratio of setup time equal to 480%. While lot size of 10,000 will take 1,048 minutes operation time per item, with ratio of setup time equal to 5%. According to the relationship between lot size and time of setup. The smaller the lot size, the higher the ratio of the time of setup. So, to apply this principle and gain from a small lot size, a true reduction of the setup should be done. Can we increase the batch size to its maximum limit without any problem or additional cost? The answer is no. Why? If we take into consideration the holding cost of the inventory. Holding inventory often comes with its own costs. This cost can be in the form of direct costs incurred by financing the storage of said inventory, or the opportunity cost of holding inventory instead of investing money elsewhere. Holding cost increases with increasing of the lot size. The total cost is the sum of holding cost and setup cost. The optimal lot size is a set point designed to minimize the cost of setup and holding costs together. So, even with this module, if we want to make smaller lot size, the total cost will increases. How this problem could be resolved. Unless setup costs are simultaneously reduced setup cost result in new total cost curve. This will solve the problem and result in a new optimum smaller lot size. Now, we will go deeper in the manufacturing system and take into consideration other factors in addition to holding and setup costs. Hence, the choice of batch size will affect both the number of setups required and hence utilization and the time spent waiting in a partial batch. Furthermore, the cycle time will be affected by whether parts exit the station in a batch when the whole batch is complete, or one at a time if lot splitting is used. The following notations will be used. K is the serial batch size. R of A is the arrival rate, parts per hour. T is the time to process a single part, in hour. S is the time to perform a setup, in hour. Since R of A is the arrival rate of parts, the arrival rate of batches is R of A divided by K. The effective process time to process a batch is the sum of processing times for K units, plus the setup time, as shown in the equation. Hence, machine utilization is R of A divided by K times KT plus setup time, as shown in the equation. So, the minimum batch size that would result in utilization lower than 1 is calculated as follows. K is greater than S times R of A and times 1 minus TR of A. The average time in Q, CT of Q, is given by the VUT equation shown here. The total average cycle time at the station consists of Q time, plus setup time, plus wait and batch time, WIBT, plus process time. CT is equal to CT of Q, plus WIBT, plus T of E. The optimum batch size is the batch size, which gives minimum cycle time. For the following process data, calculate the minimum safe batch size, cycle time for the given batch size and for minimum batch size. Illustrate and graph the relationship between batch size and cycle time and find the optimum batch size. Please pause the lecture and solve the exercise. Time to process batch. T of E is equal to K times T plus S, which is equal to 15. Arrival rate of batches, R of A, divided by K is equal to 0.04. Utilization, U is equal to 0.6. For stability, U less than 1 requires K is greater than 3.33. Minimum batch size required for stability of system. Average queue time of station, CT of Q is equal to 16.87, and average cycle time for K to be equal to 10, CT is equal to 31.87. For minimum batch order, which K is equal to 4, time to process batch is equal to 9, utilization, U, is equal to 0.9, average queue time at station is 60.75, average cycle time is 69.75. In order to draw the process batching system, we will use Excel to calculate the CT against K. Then, we can find the K of minimum cycle time, which is optimum batch size, which is equal to 8. Total production maintenance, TPM, is a system of maintaining and improving the integrity of production and quality systems through the machines, equipment, processes, and employees that add business value to our organization. TPM focuses on keeping all equipment in top working condition to avoid breakdowns and delays in manufacturing processes. The traditional approach to TPM consists of 5S as a foundation and 8 supporting activities, sometimes referred to as pillars. The 8 pillars of TPM are mostly focused on proactive and preventative techniques for improving equipment reliability. Autonomous maintenance, planned maintenance, quality maintenance, focused improvement, early equipment management, training and education, safety, health and environment, TPM and administration. Purpose of TPM is to reduce scheduled and unscheduled downtime from typical levels of 30% to below 5%. How can we do that? Assess current operating conditions, evaluate machine utilization, productivity, etc. This can be done in measure phase. First, availability, runtime, in minutes, is the planned production time minus the planned downtime, meeting, prevent maintenance, etc. Unplanned downtime, in minutes, is the breakdown in minutes, plus the changeover in minutes, plus the minor stoppages in minutes. Net operating time, in minutes, is the runtime minus unplanned downtime. Availability percentage is net operating time divided by runtime times 100. Second, performance. Processed amount is the total good and bad units. Design lead time, in minutes per unit, is the ideal takt time. Performance percentage is equal to processed amount times design lead time divided by net operating time times 100. 3. Quality. Total rejects, in units. Quality percent is equal to processed amount minus total rejects divided by processed amount times 100. 4. Overall equipment effectiveness, OEE, percent, is equal to the availability times performance times quality. 5. Failure and repair times, mean time between failure, MTBF. Mean time to repair, MTTR. Raise facility and equipment effectiveness to over 85% by applying TPM. Calculate the performance, the OEE percent, given the following process data. Does the system need improvement? Why? Please pause the lecture and solve the exercise. Calculate the performance, the OEE percent, given the following process data. Net operating time is equal to 379 minutes. Availability is equal to 84.2%. Performance percentage is equal to 91.3%. Quality percent is equal to 92.5%. OEE is equal to 71.1%, which is less than 85%. The system needs improvement by applying the TPM as follows. How to improve. Improve Phase 1, return equipment to reliable condition. Clean machine thoroughly. Place a color-coded tag or note on areas requiring repair. Record all needed repairs in a project notebook. Perform repairs. Improve Phase 2, eliminate breakdowns. Review defect tags from Phase 1. Eliminate factors contributing to failure. Improve accessibility to the part or area so you can regularly clean, lubricate, adjust and inspect. Improve Phase 3, develop TPM database. Document all preventive and predictive maintenance procedures. Improve Phase 4, eliminate any defect. Install visual controls. Help prevent future failures by training maintenance staff in proper techniques. Implement 5S housekeeping and organization. Regularly review and improve machine performance. Improve safety. Preventive maintenance. Maintenance that occurs at regular intervals, determined by time, for example, every month, or usage, for example, every 1,000 units. Predictive maintenance. Maintenance performed on equipment based on signals or diagnostic techniques which indicate any deterioration in equipment. Example for maintenance plan. Sample of TPM standard work. Please perform the activity and send your outputs by email for assessment. Mistake prevention is the ability to stop mistakes before it occurs. For example, machine operations that make it very difficult or impossible to produce a defective product. Mistake proofing is making it impossible for errors to be passed to the next step in the process. For example, systems that either prevent the defects or inspect each item to determine whether it is defective. Polka yoke systems, control or warning approach, shuts down the process or signals personnel when an error occurs. Dials, lights, and sounds bring attention to the error. Prevents the work from moving on until the process step is complete. Process stops when irregularity is detected. High capability of achieving zero defects. Prevention approach. Employs methods that do not allow an error to be produced. 100% elimination of mistake or 100% zero defects. Examples for Polka yoke system. Now, we will learn what are the 5 examination methods and the advantages, disadvantages of each method. Traditional examination. Divide into good parts and scrap rework. Reduce the defective parts delivered to the customers. Does not prevent error production. Slow feedback via scrap and rework. Statistical examination. System to reduce costs for examination. Does not prevent error production, does not ensure non-defective parts. Errors can be passed through due to examination of samples. Slow feedback via scrap or rework. Continuous examination. Every process step controls the quality of the previous process. 100% of the parts are examined. Does not prevent error production. High effort and expenses of examination efficient only for small amounts. Self-examination. Every process step controls its own quality. Immediate feedback and corrective measures stops the further processing of a defective part. High effort and expenses of examination. 100% of the parts are examined. Complete examination. Every process controls its own quality and that of its supplier. Problems are identified before the process step comes to an end. Immediate feedback and corrective measures stops the further processing of a defective part. High effort and expenses of examination. 100% of the parts are examined. Purpose of work cell optimization: to reduce the time needed to complete a task or set of tasks and eliminate opportunity for mistakes. When to use work cell optimization: whenever you have inefficient workflow, too much movement of people or materials. How to optimize work cell design: you will never get the design perfect the first time around. So, first get it in place, then use operator feedback and process performance to tweak the layout or the design. Phase 1, Pre-work. Stabilize lead times throughout the entire process. Eliminate part shortages. Make sure the process, as a whole, is meeting customer requirements, demand and quality. Phase 2, Redesign a work cell. Design the layout and the flow for multiple machines or multiple steps per operator, but typically overstaff at first. Please don't sacrifice CTQs. Decide where raw materials and WIP inventory will be located. Select a cell design, see options below, and put it to place. Apply operational improvements to reduce batch sizes. Apply line balancing principles to smooth task times. Use cell is one of the design options of work cell optimization. It is easy to see entire product path, easy for operators to operate multiple machines, material handling to from cell typically at single location, facilitates ownership of process. Example of use cell. T-cell is another design options of the work cell optimization. It is good for products requiring 2 or more sources of input. Also, it is good for cells that run 2 or more different end products with some operations in common. Z-cell is another design options of the work cell optimization, good for building around monuments, structural beams, oven and machining centers, etc., or other capacity constraints, receiving, shipping, etc. Still allows operators to manage more than one machine or operation. Redesign work cell to operate multiple machines and handle the material to and from cell typically at single location. Please pause the lecture and solve the exercise. Here is the process after work cell optimization. Thank you, and see you in the next lecture of the improve phase.